Good morning, everyone. We'll just give one more minute before we close the doors and start the session. Thanks a lot for coming this early. I know it's Thursday. All right. Good morning again. Thanks again for coming this early. It's a Thursday, and I'm sure there are a lot of other sessions you've attended. Too many things you've ingested over the past 2 days. So thanks for sparing time to attend this session on microservice architecture patterns. My name is Namit. I'm a cloud solution architect. I work for Cloud Solutions, cloud with a K. I have around 12 years of industry experience with IT. I started my career with Microsoft, was part of products team for Microsoft, delivered Live Meeting 8, Lync, Windows 7. The calculator was built by me. And I had the fortune of working with Azure from the very first day of it in market, which was back in Feb 2010. So I have delivered numerous enterprise-grade solutions on Azure. And we have the champ, another Azure champ, Rahul Roy here.
Thank you, Namit. Good morning, everyone. My name is Rahul, and I work with Redify as an Azure technology consultant. Previously, I had the opportunity to work with Microsoft, where I was the subject matter expert on Azure for worldwide community there. In the role, I had the opportunity to work with partners spread across the globe on delivering and migrating workloads on Azure. So I have plenty of experience with working on workloads. Today, the reason why we are here is because of our urge to share our learnings that we have accumulated over all these years and disseminate them to you. So what we have done here is that we have taken 7 patterns out of which are very focused on today's enterprise scenarios, and we'll showcase them to you. Let me walk you through the agenda of today's meet. So first of all, we will start by looking at what microservices are. We'll take a brief overview of that, and we'll follow that up with Microsoft Azure Service Fabric, a small discussion around it. And then we'll walk you through 7 architectural patterns that are highly relevant in today's enterprise scenarios, and which might help you design better microservice solutions on Azure. We'll finally open the floor up for Q&A. In this short journey, we'll have pit stops along our way, which are marked by these dots. And we'll play some trivia, and there are exciting prizes up for grabs.
Okay. Yeah, no marks. Yeah, so before we deep dive into the architectural patterns, I thought it's relevant to understand why even use architectural patterns. So why we are here to discuss these patterns at all. And I was actually looking for a real-world example with my beer on. When my wife decided to ruin my happiness, she offloaded me with one of her tasks of babysitting one of her friend's daughter. So I was sitting with this 6-year-old and thinking about how do I talk about relevance of architectural patterns in today's world. And then I had to take her to a modeling workshop. So the task we were given is to build a model of her favorite cartoon character. It would have been much easier if it was a Mickey Mouse or a Donald Duck, right? But this girl likes Hulk. Now, like an architect, we started thinking about what would be the end design, okay, how it should look. And then we started thinking about what would be the building blocks for this model. So being lazy and what I could find nearby, we thought, why not build a Hulk with Lego blocks, right? That's an option. So we thought, well, if the size doesn't matter, let's build it with Lego blocks. We ended up building something like this, which doesn't even closely look like a Hulk. So she was not very impressed with what we built, right? So then we thought of a second option. Why not use something more granular to build a model? Why not use something like clay, which can give you a finish, which can give you the flexibility to mold anything? Okay, so we went and bought a lot of clay. Now we quickly realized that it's not just the building blocks we require, but we also need skill to build a model like this with clay, right? You exactly need knowledge on how to model it, right? And that's a skill. Because we started building, and I built one arm and she built another, both were of different sizes. And then we had to build this body and legs which could hold the whole thing together. It was not easy. So this is a typical architectural challenge these days, right? When you have microservices, smaller building blocks, and separate teams delivering content, it is very difficult to manage and orchestrate the delivery of a bigger solution. A very typical architectural problem. So how did we finally solve it? After working on 3 hours, on this for 3 hours, and terribly failing, we tried to Google it, or Bing it rather, and figured out that some genius has already solved it. You just need to use a mold. We went to the nearest shop, got a mold, put the clay in, punch it, and we got the best Hulk out. The mold here is like an architectural pattern. The problem we were trying to solve was already solved by somebody using an architectural pattern. So all we need to do is to repeat that pattern which was proved and tested. With that example, let's quickly look into what microservices are, right? For people who already have worked with microservices, this is going to be a very quick refresher. For people who have not, my friends who have not, this would be an introduction. This is a level 200 session, so it's just going to introduce microservices from an abstract perspective, right? In this subsection, we'll look at what microservices are, differences between its nearest relative, service-oriented architecture, right? We always have this question, why do people keep changing technologies, right? Every 10 years. Last decade, it was service-oriented architecture. The year I was born, it was object-oriented computing. Why just keep changing things? And then we'll look at benefits of microservices and look at microservice hosting platforms. Like once you've built the microservices, where to host these microservices together, right? So the best definition of microservices that I could find on web is this, right? It's an autonomous software which is built to perform a single specific granular task with properties like hyperscale. Because as your services are smaller in nature, you want to do high density deployments, right? So that you can utilize the hardware resources underlying. You want to deploy as many services you can on the single box. You want it to be technology agnostic because the team who is building the microservice should not be cognizant of who is consuming it, what technology he's using. Same way, an application developer, probably who is using Java, should be able to consume a web service which is developed in C# or any other language. It has to be autonomous. A microservice has to have the efficiency of executing in its own isolated process space, right? It should be deployable independently, manageable independently, decommissioned independently, etc. It should support versions because it's in a typical enterprise scenario, it happens that you build a microservice, probably which adds a number. And there are multiple consumers of this microservice. Each of those consumers may have different capabilities, to cater which you'll probably have to have different versions of the microservice running simultaneously. So supporting versioning is an important property. It should be decoupled. This is aligning to a famous architectural principle of minimum knowledge, right? So being a microservice, I should be only cognizant about what work I am doing within that microservice. I should not be bothered about what's happening outside the world. And it should be focused. So this is focused and elementary. So this is, again, obeying a famous architectural principle called as principle of single responsibility. A microservice should only be aligned to one responsibility. A microservice should be independently manageable and, of course, uniquely addressable to be able to reach it. Now to look at the differences between the predecessor and microservices, let's invite Rahul.
Thank you. So this is one of the questions that we frequently get asked by our partners. Why we should use microservices over SOA or service-oriented architecture? To explain the answer better, let's take a look at one of the real-life implementations of it. I won't dig deep into the implementation, but this is one of the implementations that a car rental company has actually done for building their systems. So as you can see, there are several components in this system which are talking to each other through an integration platform, which is generally Enterprise Service Bus, which they use. And there is a POS portal installed at retail locations through which all these the services which these backend systems provide, they are rendered there. So a few of the limitations of using SOA to build systems is that these systems are tightly coupled the limitation is that these systems are tightly coupled as according to how the various parties in an organization communicate. So for instance, there is a reservation and a corporate office service. There might be two units handling them separately. How they communicate is normalized by SOA by using Enterprise Service Bus in between. The cost of change in making any change in this system is very costly because there are numerous parties involved. For instance, if you even need to change the backend service, the backend database of, let's say, the corporate office, it would incur changes in the integration platform, and all the services which are consuming data of this service would need to undergo changes as well. Versioning is very difficult thing to attain in a SOA-based system because the services, they need to maintain backward compatibility until all the clients upgrade their services and reach a particular level. The Enterprise Service Bus that we have involved in between, it risks becoming a monolith because it has ingested in itself all the transformations and translations and protocol bindings in itself. Next, let's see how we are going to solve this challenge using microservices architecture. So basically, we can split the architecture that we saw previously into 3 separate domains. We can have services deployed within these domains, and they can, in turn, talk to each other. The obvious benefits that this architecture gives is that each of these services that you can see within a domain, they are independently scalable. They don't rely on each other because they are separated by domain boundaries. You can scale them independently. These services can communicate to each other rather than getting integrated through an Enterprise Service Bus or an integration platform. These services are domain focused, so the teams that are organized building these services, they are not centered on technology, but they are rather focused on delivering a piece of functionality within a particular domain. It's easier to adopt continuous integration and continuous deployment systems in these, and it offers a better versioning strategy than SOA systems provide. So Namit, now that we know why microservices are the preferred platform for building are preferred over SOA, can you walk us through a few hosting platforms
Sure.
for microservices?
Yeah. So there are different ways of hosting your microservices. The bare metal way, when you can have a physical machine on your desk or on your data center, and you dedicate it for hosting microservices. You can use virtual machines, which can run on bare metal machines. You can use the new buzzword, containers, right? Just host microservices within containers, or host them within processes. Now, each of these mechanisms give you different level of isolation, maybe hardware isolation, kernel level isolation, or resource level isolation. So obviously, you can see that if you host a microservice within a physical machine and you dedicate that machine for that microservice, you get maximum isolation. Nothing is shared. If you host it in a virtual machine, of course, the hardware is shared because there are multiple virtual machines running on one physical hardware, which hosts multiple microservices within. If you use a container, because containers are OS-level virtualizations, the kernel is also shared across different microservices. If you use processes, everything is shared. Like you can use, the hardware is shared, the kernel is shared, and so are the resources. This is most flexible, but it comes with a caveat, right? When you deploy microservices on processes, you need to be cognizant of the starvation which may occur. So if you have 15 services running on one box, which shares the resources, What if one service starts getting a lot of load and it starts consuming a lot of resources? The other services will get starved. So there are patterns which can be applied to stop this from happening. We'll discuss few of them later in the session. A first trivia for a first set of gifts. Why are microservices represented by hexagons? Anyone? Not you, Simon. Partially, yeah, partially.
Good enough.
Do you know? Yeah. So, yeah, so they're based on, oh, sorry, you had an answer? Okay, yeah.
Yep.
Yeah, that's the right answer, right? So basically, microservice deployments are based on hexagonal architecture. It's a very famous architectural pattern where the code basically is insulated by a hexagon, which opens up ports and adapters. This pattern is also known as ports and adapters. So every time you need to talk to a microservice, you need to write an adapter to a port. And those architectural patterns are represented by hexagons. So and which inspires microservices, and that's how the hexagonal architecture. Yeah. Thanks for the answer. I'll pass on the goodie towards the end of the session. Yeah. I think there is another question Rahul had.
Yep. So the question that I have for you is, according to Conway's law, which factor drives system designs in an organization? Let me show you the hint.
Yeah.
So it's how two parties in an organization interact is what drives the system design, according to Conway's law. Yep.
Yeah, that's the answer. Yeah. Thank you.
Good enough. Thank you. So now that we have completed our first lap of journey, let's look at the Microsoft's offering for hosting microservices, which is the Microsoft Azure Service Fabric. So in this section, we'll slice the Microsoft Azure Service Fabric cake and look at the goodness layer by layer. So we'll first start with looking at what actually is Microsoft Azure Service Fabric and why we should use it. Next, we'll look at the role of Microsoft Azure Service Fabric as an orchestrator of microservices. Next, for us programmers, how does it make sense? So we'll look at the application model and the programming model of Microsoft Azure Service Fabric. And finally, we'll look at a few of the patterns that we were talking about. So let's start with what is Microsoft Azure Service Fabric. So how MSD and documentation puts it is Azure Service Fabric is a distributed system platform that makes it easy to package, deploy, and manage scalable and reliable microservices. Now let's split this definition into parts and see how, and try to make sense out of it. So Microsoft Azure Service Fabric is a distributed platform, which means that it can deploy and host, basically it can host several independent microservices onto itself. It's portable. So it doesn't matter where microservices live. They can live starting from your laptop to your data center, to Azure, to Amazon Cloud or Google Cloud. It doesn't really matter which data center you use. You can, if you host your applications on Service Fabric, they can live anywhere. It's a self-healing platform. So if any piece of hardware, any node in the cluster that is provisioned using Service Fabric goes down, Service Fabric has the capability of moving your applications around so that they are highly available. It supports agility of delivering microservices. It supports CI/CD natively, so you can build your applications on it without in an agile manner. Next, it supports application lifecycle management out of the box. So tasks such as designing, deploying, managing applications becomes very easy when you're using Service Fabric to host your microservices. again, it's OS agnostic. It doesn't really matter whether your microservices are built and deployed on Windows operating system or Linux operating system. Service Fabric is portable enough to work on both the platforms. It is self-managed. So there is an intelligent piece of software that runs on top of that runs as part of Azure Service Fabric that manages where your applications and microservices are going to reside. Next, we know why we should use what Service Fabric is. Let's take a look at why we should use Microsoft Azure Service Fabric. So the obvious advantages that Microsoft Azure Service Fabric offers is the scalability. So you can scale your microservices deployed on Service Fabric to the nth level. State maintenance. So it's one of the typical challenges in microservices of where they store the state data. So Microsoft Azure Service Fabric allows you to bring your state near to your applications. So the state data actually resides with your application. This improves efficiency and also helps make state management very easy. You can have n number of applications deployed on a single VM. This optimizes the infrastructure. Again, as I said, it's technology and platform independent. Most popular programming languages are supported natively by Azure Service Fabric. So you can be a Java developer or .NET developer. You can build your applications in your preferred language, give them to Service Fabric, and it should be able to host them. It is fault tolerant. Any piece of hardware going down at any point of time or your application failing, it has provisions in place to make the system work. Would you like to talk us through how Service Fabric would act as an orchestrator of microservices now?
Sure. Yeah. So one of the key responsibility of Service Fabric as a platform is to orchestrate microservice deployment. So orchestration as a term is not new to microservices, right? We have been developing orchestrator as a component for decades, right? So how do you define orchestrator as a piece of software, right? It's a software used to manage deployments, a piece of software which is supposed to abstract the complexities behind resource management of microservices. And the way Service Fabric does resource management is by a process called as load leveling, right? Let's look at how Service Fabric levels the load across multiple clusters and multiple microservices at runtime. So what is the typical process of setting up a Service Fabric cluster? First, you have to dedicate some machines. Bring up 5 machines or 6 machines or 50 machines. Each can be of a heterogeneous configuration. One can be very capable, 50 CPUs, 500 GB RAM or whatever. One can just have 1 core and 700 MB RAM. One can run Linux, one can run Windows. Once you dedicate this machine to Service Fabric then installs a layer on top of that and then hosts microservices on it, right? So in this example, we have dedicated 6 machines to Service Fabric named from N1 to N6. The first thing Service Fabric does is to install an agent in each of these machines. This agent is used to talk back to the machine, check its health, check the status of how much of resources consumed, etc. And then it installs its cluster services, which are used to manage the microservices, like the scheduler, the resource manager, etc., right? And then it opens up the stage for you to deploy microservices. So in this example, we have deployed 7 microservices. A, B, and C microservices are deployed on N5. N6 holds microservice D, N4 holds E, N3 holds F, and N2 holds G. What happens in action is that once a service is deployed, the agent installed on each box will constantly check the health of this microservice and the resource consumption on this box. And it will then report it to the cluster manager service installed within the same cluster. And then the cluster management makes cognizant decisions about how to balance the load amongst the virtual machines which is allotted within the cluster, right? Let's take an example of how the third step works in detail, right? One of the examples which I would like to share is when we were developing a solution for a North American pizza delivery customer. It's usual that during Super Bowl time, the pizza delivery request increases, right? So imagine a scenario like that where, say, there is the microservice A which takes care of generating orders for pizza or processing orders for pizza. And then there is a Super Bowl event coming up, and A starts hogging all the resources on that box N5, which leads to starvation of resources for microservice B and C because A is taking a big load. How Service Fabric handles this situation is when the load consumption is reported by the agent to the Service Fabric cluster manager. Service Fabric cluster manager then queries rest of the nodes for how much of resources they have to spare. And then it makes a cognitive decision on which node it can displace the service to, and then slowly move that service to another node without impacting the quality of service or without degrading the performance. Right? What you can see here is this is very typical to Service Fabric. Right? This is not load balancing. This act is called load leveling. So with existing resources, you just shuffle the microservices across the resources to make maximum utilization of your resources as underlying hardware resources, right? Let's jump into the application model now.
So now that we know how Microsoft Azure Service Fabric acts as an orchestrator of microservices, we as developers, we are more concerned about how we are going to deploy our applications on top of it. So let's look at the deployment view of an application that is to be deployed on Microsoft Azure Service Fabric. So an application in Service Fabric is composed of a number of microservices. Each of these services is made up of three parts: code, which contains your application binaries; the configuration, which contain data such as your connection strings, other secrets; and data. Data can contain static data which can be consumed by an application. The important thing to consider here is that code, config, and data, they can be independently versioned and deployed. From a logical viewpoint, an application is again made up of services. These services can be either stateless, that they don't store their state anywhere, or they store their state externally, or stateful, that they do store their state, and that state lives close to the application. It actually resides in the same VM. The state can be split into multiple partitions to improve efficiency. And each partition can then, again, have replicas to ensure high availability. So one of these replicas would be the primary replica, which serves the data for CRUD operations. Other replicas are secondary, which can be promoted to primary in case of failure.
Yeah, so now we understand the logical view of Service Fabric applications. What are the types of packages which Service Fabric supports, right? So you can package any executable and throw it to Service Fabric, a calc application, notepad, anything. Package it as an executable, throw it to Service Fabric, let it know that you want to host it like as a guest executable, and say that I want 15 instances of it. Service Fabric takes care of taking this bundle and deploying it across machines as 15 instances. You can also deploy your applications into containers and then throw the container at Service Fabric. Say that this is my container, I want 15 copies of this container. Service Fabric takes care of replicating the containers across your cluster. A more tightly, programming model which is more tightly integrated with the framework is using reliable services, where you use Service Fabric SDK to build your applications. This has many benefits because Service Fabric is now cognizant of what your microservice does because you're building it using your SDK. So health monitoring is better. It knows when your service is sick. It knows what to do if your service is not doing well, probably restart the service or bring it up on a different node. That supports two types of services, stateless service or stateful service. Obviously from the name, stateful services have data close to them. Stateless services are depend on an external state store or do not store state at all. Have you heard about actor programming model, which is like the new cool thing in the world? Yeah, so actors are single-threaded processes, right? And they're based on a virtual actor model, which is one of the product of Microsoft Research. Service Fabric also supports an actor programming model. Now, before we jump into the crux of the presentation, which is the actual architectural patterns, we would like to give you a brief overview of how we have categorized the architectural patterns itself, right? So we found out we could jot out 21 architectural patterns which are relevant to microservice deployments, and we have categorized it into 3 buckets. One, optimizational and non-functional patterns. These kind of patterns are they don't bother about what's implemented within the the microservice code itself. It talks about concerns related to, which are common to microservices like resiliency, security, performance, scalability, availability, resource utilization, etc., which doesn't really care about what the code is, but cross-cutting concerns across the services. Then we talk about operational patterns, which are relevant after the microservices are deployed, right? Once it's deployed, what are the challenges encountered while to manage the microservice itself? And then finally, implementation and functional patterns, which is more relevant to the developers about, talks about communication, abstraction, persistence of data onto the data store, etc. Second set of trivia. What's the code name for Azure? Yeah. You get the first prize. What was the code name for Azure before Red Dog? It said that Dave Cutler and his team went for a drive to some remote place to think of a good name, and they came up with a name called as Pink Poodle. Don't know why, but Pink Poodle. So obviously the legal team didn't really appreciate it, so that's why it's Red Dog. Yeah.
Yep. So the second question is, what does this icon, which is that of Service Fabric, what does it signify? Should be pretty easy to make out. I think you already gave an answer, right? Yeah. Yeah, correct.
That's
so
right.
5 nodes together making up a cluster. That's right. So you can collect your goodie from us after the session. So now we are on our final lap of the journey, which is the most important and the most exciting one. So here we will discuss 7 of the most important architectural patterns that are very useful in today's enterprise scenarios. The 7 architectural patterns that we would be discussing today are compensating transaction, API gateway, high density deployment, circuit breaker, auto scaling, and even sourcing.
Oh, probably you have one more, yeah.
Sorry for my maths. The last one is remindable actors. So let's start with the first one, the compensating transaction problem. So microservices are of polyglot nature, which means that each microservice generally has its own supporting database. This makes implementing transactions across all the persistent stores of the microservices very difficult, because the data needs to be consistent and you still want to implement a transaction. The solution for this problem is to first follow an event-driven architecture, where each service, when it makes changes to the state, it publishes events which other services can listen to and make changes to their own state. And those services will in turn emit more events which other services can consume. But this comes with an added complexity of messaging systems, such as poison messages being sent to other services, messages getting lost in transit. So another alternative is to use a compensating workflow. So the workflow would actually manage calls to microservices in order to make a transaction. If at any point one of the service fails, the workflow would start triggering the compensating logic by calling the compensatory code of the corresponding microservices. Let's see how this works by looking at a demo. Let's start by offering our prayers to the demo gods that this demo works.
Yeah, that's me and that's Rahul. Yeah.
That is someone. Excuse us for our UI skills, they're not too great.
Yeah, black and white.
Yeah, that's what works. So let's say there's an Avengers meet happening, and Tony Stark is invited. And the meet is happening, where should it happen? Let's say in the beautiful state of Kerala. And because Tony Stark is rich, he has $600 in his wallet. He wants to book a hotel and a flight ticket to complete this transaction. So let's start by making his booking. So as you can see, the first step of, so the booking has started, yep. So the first step has completed. We have been able to successfully book a hotel for him, and then a flight, and his wallet balance comes down to $300 because hotel costs $100 and flight costs $300.
Now, behind the scenes, each of these, sorry to interrupt.
Yeah, no problem.
So behind the scenes, each of those actions are actual microservices deployed on Service Fabric, which is being called one by the transaction manager. Go ahead, sir.
Yeah. So now let's take another example where a compensatory action would get kicked off. What's the name of that poor Hulk guy?
Bruce Banner. Bruce.
So Bruce also wants to go to Kerala, but since he's not that rich, he has only $150 in his pocket. So let's try to make a booking for him as well. So the booking action has kicked off. We have been able to successfully book a hotel, and he's left with $50 credit in his account. But flights cost $200. So a compensatory action has been kicked off, which reverted the amount back to Bruce's wallet, and he ended up saving money and not going to the Avengers meet.
So what basically happened was, because it couldn't complete the transaction, it reversed the previous transaction step 2, and you can see that the wallet balance got back to $150.
Yeah. So a few of the considerations that you should be aware of while choosing this pattern is that there might be timeout scenarios. So you're making calls to the services, but they're not failing. You shouldn't automatically start triggering a compensating logic as soon as there are timeouts. You should retry. Idempotency, you can, once you send a message for either a transaction to complete or to compensate, your logic should be idempotent. There should be sufficient data either for the transaction to complete or to revert. And you should have retries in place. This fits scenarios where you want to implement transactions. The next pattern.
Moving on to the next pattern, API gateway. This is, again, a very famous pattern. So driven by the very nature of microservices, they have to be really granular in nature. And quickly you will see that for an enterprise which follows microservice architecture, the number of microservices grows from 10 to 100 to 10,000. This leads to a lot of complexity around managing these services, right? The complexities are basically twofold. One, to the application which is actually consuming the microservice. They'll have to figure out where the microservices are deployed, discovery of the microservices, and then they have to catalog the microservice and then use those microservices, stitch them together to achieve an end-to-end business scenario. The second fold of the complexity is around the microservice management team itself. So if I'm a team which is building microservices, I need to cater for different application demands, take care of transformations, take care of security for different application vendors. Like say, one vendor want to authenticate to my microservice through certificates, the other guy want to use JWT tokens, another person wants to use API key. And then also about type of responses, right? Somebody would like to consume it as JSON. An old application wants it in XML. So being an application developer, should I be bothered about all this? Or should I be focusing on writing business logic for my customer, right? So what this pattern does is to separate out all these cross-cutting concerns out and then let your development team focus on writing business logic, which is most valuable to the company, right? So a pattern which solves this problem is to introduce a layer of abstraction, which is also called as a service facade, in other words, which actually abstracts out all the complexity of managing these microservices and acts as an orchestration layer. A very good example of this implementation is Microsoft API management. And let's quickly look at a demo of API management in action. That's not API management. So what we've done is we've written a very simple
Duplicate.
microservice.
Window P.
Mouse.
Window P.
Sorry for that. So we've written a very simple microservice which actually manages an employee. So we have three operations. We have a get, we have a delete, and we have a post. So we have already entered some employee details for the ease of the demo. And I can just say we're big Marvel fans, so you enter an alias of an employee and it'll return me the details of that employee. Here, IM is the alias and it returns the name Iron Man, alias IM, designation geek, pay level 1. So this is the detail of that employee, right? Now you can see that the response is coming as a JSON. Now this is an unauthenticated service. Anybody can hit it, right? It's just the code which handles the particular business logic that the developer has written. Now let me consume this API into API management, which is already done. The way I can do it is I can import a Swagger link. It shows me an existing API. I'll be able to import this API into Microsoft API management and then add policies to it, right? So we have pre-populated some policy for the ease of demo. So if you can see, I've added two policies to it, right? So I've added some authentication logic to this API. I've said that I want the policy to ensure that there is a JWT token in the header of this API call so that I can authenticate this particular request. I've also added a logic for transforming the response, saying that one of my application developer wants the responses in XML. They don't want JSON because they're a very old legacy application. So I've added a policy here which says that in the header, if I have a tag called as application/XML, then I'm going to return an XML instead of JSON. Otherwise, I'll just return JSON. So all this information is actually coded into the gateway and not into the microservice itself, right? And it's easily manageable outside the microservice business logic. Let's see this in action now. So if I go to the developer portal and click on the API which we have registered, you can see that it has automatically pulled out all the APIs which are published in this portal. And you can also get the code to call these APIs, right? If you see, you get the C# code to call this API. You can just copy paste the code onto your Visual Studio solution, and then it will run like a charm. Same with Java, JavaScript, Objective-C, PHP. I don't know who uses that, but yeah. So the portal gives you a lot of flexibility in consuming these APIs. So let's try this API, which is a getter. And pass in the alias, which is IM, and try to hit it. You'll see that I got an unauthorized exception now, because my API is now protected by an authorization token, which is a JWT, which I can pass and see what happens. the call succeeds, and it returned me a JSON response. Now let's go to the next policy. What if I want the response as XML? What I need to do is just add another header. You'll see that now the response magically turned into XML. Very simple operation. If you had to hand code this into your business logic, imagine the complexity an API developer had to go through. Back to our presentation. While using this pattern, we do have some considerations which we should be aware of. It is, of course, another layer in your architecture. So introducing another layer does come up with some performance impacts, as well as manageability impacts. You have to be careful that the API management is logging interleaved with your application for better troubleshooting, so that there is centralized diagnostics. So if something goes wrong in the API layer or the gateway, you're easily able to troubleshoot it. And of course, abstracting what microservices actually does with a layer leads to some level of filtering the information. So I don't know what are the exact parameters, probably because it's covered up by another layer. So there is a little level of information which you are missing out on, which comes with any layer of abstraction. Typical scenarios is developer-focused and analytics-driven applications. When you're coding APIs which you sell, right? Which you want quota managed, which you want to be cached, which should cater to different applications with different capabilities. This is an ideal pattern to be used for that. Moving on.
So one of the key challenges that we encounter while developing microservices is how should we optimize the infrastructure on which we are hosting microservices. So traditionally what happens is that when we code a solution, we choose a VM and deploy it and deploy our services to that. But in a typical application, there can be hundreds of microservices that are sitting behind the application. So are we going to use hundreds of VMs to build and deploy each of these microservices? I think that would be a very cost-inefficient way of hosting microservices. So the solution to this problem is to have an orchestrator in place which manages your hardware. So the orchestrator knows that you have n number of nodes available to you and what these nodes are capable of. That some of those have low capabilities, such as they might have low disk, low memory, while as others have a different set of capabilities. The orchestrator should be able to manage your deployments in a way that it moves microservices which require similar set of configurations to a particular VM and then load level them. So as and when need arises, it should be able to move the microservice instance between nodes. Jumping on to a demo. So Azure Service Fabric already has a provision in place to orchestrate your microservices. There is an intelligent piece of software that sits inside your cluster managing your microservice placements. So for instance, we have deployed a very dense application with 100 partitions and 3 replicas. That makes it a total of 300 instances on a 5-node cluster. So on this, you can see that on every cluster, if you drill down the replicas, it's not even able to show you all the replicas that are in there. And they are all spread across the nodes of the cluster.
So that's actually 300 services running on 5 machines, right? 300 web services running on 5 machines. That's a lot of scale, and how Service Fabric intelligently makes sure that the load is leveled. If one machine goes down, it takes the load on that machine and divides it into the rest of the 4 machines. Everything is taken care of by Service Fabric. The deployment just takes 3 minutes of time.
So in the previous example, we demonstrated that a single cluster is hosting a very dense application. But if we are very sure that the cluster can host many more because the node the node is capable enough to host more, we can add more applications into the cluster. And the cluster manager should be able to orchestrate between them. So a few of the considerations that should be in place while you're choosing this pattern is that there should be an isolation between the services. So services should be contained within a boundary, and Service Fabric ensures that your services do not cross their execution boundaries. There might be cases of resource starvation because there are so many microservices, each of which are independently processing data. The cluster manager should also help you ease your release management. So it would make a pretty inefficient system if you have to go and deploy your applications on each and every node in the cluster. The cluster manager takes your application binaries, places it in one of the nodes, and they get automatically copied over to all the nodes in the cluster. Some of the scenarios where you would want to use high-density deployment is where you want to deploy your applications at a scale in an enterprise in a cost-efficient manner. Also, when you're doing hybrid deployments, wherein many of your microservices are co-located in a cluster, you would want to use this. Of course, it improves performance, reduces costs, because you can target your microservices to a particular cluster configuration. Let's move on to the next scenario.
Circuit breaker has a pattern. It is not unique to microservices, but it's very useful for cloud deployments, right? Especially when we are deploying our services on commodity hardware, which has to be designed to fail. So you have to, one of the primary principles for developing across developing on cloud is to design for failure. Now these failures are of different types, right? Most of the failures are transient because your virtual network goes down, or there's less bandwidth available for your application. Maybe the hard disk failed on a virtual machine. Any cloud operating system, say like the Fabric controller, is capable of bringing a new node up or fixing this issue faced by your application in no time. So these faults are transient. And there are patterns which can be used to work around these faults, like retry pattern, right? If there is a transient fault, you employ a retry pattern on your application. I keep retrying, calling the service, and if there is a transient fault, probably the second or the third call will pass through. Now, but there are some failures which probably will take a little longer. So we were implementing a solution for a weather service, right? Now, instead of just calling a system which would give the weather service, this service was actually talking to IoT devices, which would sense the humidity in the room and then respond. Now, what if that sensor didn't work? Does it make sense to retry, keep bombarding the service? Because the service may take 5 minutes to time out, which means that if I have a retry logic which will try 10 times, 10 times I'm going to keep hitting the service, which can cause different problems, right? The problems can be that if you keep hitting the service, you may prevent it from recovering itself because there is constant load on the service itself. It can also lead to cascading failures because because of the load, it may then end up failing your load balancer because there's a big queue. So what's a good way to handle it, right? A good fix for this problem is to have an abstraction layer, a proxy in between your microservices and your application which is calling this microservices. What does this do? It actually acts like a circuit breaker, like a fuse, right? So the first time your application hits a service and if the service is down, your circuit breaker is cognizant of what happened. Then it's gonna open the circuit and then not let you go to the service unless that service is up. It can execute compensation logic and give you some default values. So in case of the weather service, it would just give you the last weather which was reported, right? That way, you save a lot of time and experience and performance by not really hitting the service and also giving time for the backend service to recover. Let's see one of these examples in action. So what we have done is we have coded a weather service, which is
open.
on the, yeah, that's a simple web API deployed on app services, which actually returns random weather. And we've created a dashboard which shows you the weather, right? So if you can see this, this refreshes every 10 seconds. It randomly throws a weather status. Let's wait for it to refresh. Yeah. So it's 29 degrees. What we are also logging is the turnaround time for this response, right? From the time I fired the request till I got a response, what was the duration of the call? So in the last call, it was 2.2 seconds, right? Now let's see what happens if we stop this service. And what I'm trying to emulate is that there is a failure on the device or something went wrong in the service, and we need time to recover that, right? So let's stop this service, and let's see what happens. It's still stopping.
Yep, takes a little bit of time.
Oh, so it failed, right? You can see that the call failed to that service, and it took 0.4 seconds for us to figure out that the call timed out, and we responded. I'm going to pause the polling for a minute and explain what happens and how the circuit breaker logic kicked in. You can see the first failure, it took 0.4 seconds to figure out that the service was down. And then the circuit breaker kicked in and figured out that, oh, there is a failed service. Why am I even letting it go to that service? I'll cut the fuse here. It cut the fuse, and the second failure you got in 0.002 seconds, which is 200 times of optimization in performance. So from a calling application, what you see is, first time it failed, your retry logic will now hit the service again, and you'll get a response in no time, which is a great, which is very efficient performance itself, right? And what happens if you, say, switch on the service again? I'll have to refresh it because
Also, the circuit would stay tripped for 30 seconds. So any subsequent requests that are made within that time interval, they won't actually go and hit the service itself until the timeout period in that circuit breaker has elapsed.
So once the circuit trips,
Yep.
Yeah,
back.
so we can pause. Yeah, so the service is back, right? So once the circuit trips, how the circuit breaker knows that the service is back up, right? So there are two ways to do it, right? The easy way is saying that for next 30 seconds, I'm going to assume that the service is down. And on the 31st second, if I get a call, I'm going to let it pass through. If it fails, for another 30 seconds, I'm going to wait. There is another way of doing it, which is when you hit a call on circuit breaker responds with the last status, but also asynchronously calls the other service to figure out if it is up, and asynchronously updates the state of the fuse so that you save a lot more time. In this case, it's just a 30-second kickoff. Going back to the things we need to be aware of while we implement this pattern. Again, writing another layer in front of your applications, which even if it's like a proxy attached to your application, it comes up with a little bit of performance impact because it's one hop. You need to exactly know what should trip the circuit. It's very important to understand what exception should trip the circuit. What if it's an application exception? Should you trip? You should not, right? Because you should only trip on service failures. You should be cognizant of what you're implementing the circuit breaker against. And also, when you implement this pattern, you need to ensure that this pattern itself can tolerate concurrency. It should not become a bottleneck later that a lot of applications are trying to access a circuit breaker, and that itself fails, right? So these are few of the considerations you should be aware of. Yeah, scenarios are like high-performance reactive system, which needs to know as and when things fail, so that the UI can be responded and people can be alerted of a service failure. Moving on, auto-scaling.
So scaling is not a new challenge. You must already be aware of it. So loads on microservices can come on any time, right? And your microservices should be ready to respond to them in real time. So if you don't have an auto-scaling solution in place, it might lead to resource starvation of services. And your service should be able to handle unexpected load. That's what I already talked about. And also, it should do so in a cost-efficient manner. So you shouldn't have to provision n number of resources beforehand in expectation of load. The solution, an ideal auto-scaling solution, should be parameter-driven. So based on metrics that your machines are capturing, load leveling, an auto-scaling solution should be able to make decisions on top of that. And it should be able to decide, it should base those solutions based on a number or within a range of the metrics that it has captured. So throwing more instances of the same hardware is not always the solution. You should always also think about how you can upgrade the hardware in order to serve requests. So let's walk through the steps when you're trying to configure auto-scaling in a service fabric cluster. So first of all, a service fabric cluster is composed of a number of VMs participating in a VM scale set. So you need to provision it, enable diagnostics on top of it, and set the metrics on which you want to scale, which can be CPU performance or number of user requests. Then choose a min and max count of those values. That if the value passes this or falls below that number, then a scaling decision should be made. Then choose a polling frequency at which these metrics should be polled, and then choose an aggregation technique such as sum, average. Then pick an operator greater than or less than, and then set a threshold of the value. Then pick a direction of the scale, whether you want to scale in or out, and then set a cooldown period because scaling decision takes a while to kick in. Now let's look at a demo. So here we have simulated an auto-scaling decision. So we have a node in place, which is in disabled state to emulate a new node is available in the cluster.
First one.
Yeah, we are just going to activate it to simulate that this node is going to join the cluster. And once this node has joined the cluster, you can see that all the services, they have been provisioned in this new cluster, and now they're working fine. The Hello World service with 300 instance that I demonstrated previously, they've now been placed, a few of the replicas have been moved because this new node is available in the cluster now. Can you move back to the demo machine? So system downtime, scaling decisions, and basically the cooldown period that I talked about. These are all the points that we need to take into considerations when we are building an auto-scaling solution. And also we need to take care of the step size, how many instances we want the count to increase or decrease by. Login monitoring should be centralized. Scenarios is where the workloads are not predicted. You can use this solution to scale your microservices.
So event sourcing is a pattern which we wanted to discuss, but we'll probably skip it for the benefit of the time, because event sourcing is a common pattern and which is not really specific to microservices. But just in case you're interested to talk about event sourcing, please come and talk to us after the session. Happy to explain it to you. Yeah.
So this brings us to our final pattern that today we are going to discuss. So rather than looking at these pictures, actors are very easily simulated by human beings. So for instance, you are going shopping. Would it make you an efficient shopper if you go to the shop, pick an item, come back, and then go to the shop again, pick another item, and come back? No, the experience would be really very bad, right? So that's the problem. What would be the solution? The solution would obviously be to have, let's say, a number of items written on a post-it note and maybe stuck on your shirt so that when you go to the store, you can take an atom off, pick it from the shelf, do the next work, pick the next item, and then come back home collecting all these items together. So that's what we are simulating here. So in Service Fabric Actor Framework, if there are any long-running operations, then what you can do is that on receiving a request, you can set a reminder in the application. That reminder would trigger off and return the response to the caller immediately. The reminder would trigger off after some time, and the action can be performed by the actor, and the responses can be aggregated in a separate store. This state store can be invoked from time to time by the calling application to show the progress. Let's take a look at this demo in action.
While the demo is being set up, because Actor Framework is fairly new, just wanted to explain why this pattern is relevant. Actors are single-threaded processes. And that's why this pattern is more relevant, because the moment you enter a single-threaded process, you are stuck until the thread is complete. Right? And that's the challenge we face, because you talk to actors, and the actors take its own sweet time to respond. Your UI is stuck. So that's yeah. You want to go ahead with the demo?
Yeah. So going ahead with the demo, let's say, so here what we are going to do is we are going to trigger a long-running process. So Skywalker wants to count the number of black pixels in this image. So we have triggered the process now. So what it is doing behind the scene is that it is setting up a reminder to count the number of pixels, and behind the scenes, a long-running process would get kicked off.
So what happens is that this process, which is actually counting pixels, is a really long-running process. It goes pixel by pixel, count it, and see if it is black and responds it, right? So if you have to wait till the whole operation is complete, that'd be like 2 hours. So the remindable actors pattern actually keeps updating a different store and emulates asynchronous actor calls.
As you can see, the count here is increasing asynchronously because this operation progress is stored in a separate store. And that store is queried to return the most updated response there. Switching that to demo. So a few of the considerations that you should keep in mind while using this pattern is that your actor itself needs to be fault tolerant. And since reminders are nothing but just a message, so you should have the capability of handling poison messages. It's not a replacement of scaling. You still need to have scaling in place. Some of the scenarios where you can use it is when you want to build a better UX in an actor-based application which involves long-running processes. It, of course, improves efficiency. Yeah. So a brief recap, we took a look at the microservices. We took a look at the most ideal platform for hosting microservices according to Microsoft. And then we took a look at a few of the architectural patterns. The floor is now open for Q&A. Some mandatory slides. Do you want to talk about this one?
Yeah, so we've identified 21 patterns, and we've discussed around 6. So in case you are interested in knowing more about patterns, please go ahead and, we have a book written. So, and yeah, we offer a 40% discount on the book for anyone in this session. Meanwhile, yeah, any questions, anything else you wanted to know about Service Fabric, microservice patterns, implementation, our past experiences in implementing microservice patterns? Yes, please go ahead. Yeah, so you can, because it's operating on a VM scale set, right? Azure Service Fabric runs on a VM scale set. VM scale set natively lets you scale up. So you can do it from the portal. Can you open a? Yeah. 6. Yeah. So what you see here is a Service Fabric cluster, right? And if I go to the resource group.
So cluster is nothing but a set of nodes that are participating in a VM scale set. So you have the capability of having the scale set scale up and down as well. So you can choose what configuration you want to use. So here what Namit is doing is he has chosen the scale set And not only can he increase the number of instances in that scale set, he can even change the size. Yeah,
So
these are all the configurations
so
available.
I'm using a D1 machine here. But if you want to scale to F16, 16 cores,
Yeah.
feel free to pull it down. Yeah, you can. Today you'll need to write some code. It's not a slider. But yeah, you can do it using partial, CLI, C#. Yeah. Any other questions? Cool. Thank you. Thanks a lot, sir.